Hi, grade 12s. So I am working through number 10, day number 10, worksheet number 10 off of my website. And this corresponds to around page 400, which is chapter, let me see, sorry about this. I should have had that 8 point something, 8.2, the equilibrium of weak acids and bases. Okay, so we're looking at polyprotic acids and bases. Obviously, we shouldn't call it polyprotic bases, but if we're looking at this example of phosphoric acid, you can see that we have Ka1, Ka2, Ka3, and it corresponds to how many hydrogens are in the original undissociated species and how many hydrogens are lost. So in this first example here, this is the first time we get an anion, and we have the largest Ka value. As this ion, as another hydrogen is lost, you can see, look at the difference. It goes from 10 to the minus 3 to 10 to the minus 5. So it does not want to lose another hydrogen. Think about it. It is a negative anion trying to lose a positive cation. It doesn't want to do that because of the law of electric forces. Just for that, there's the attraction, electrostatic attraction. So a negative anion is not going to want to lose something that's positive. And then the final loss of a proton, it is very, very tiny amount, 4.2 times 10 to the minus 3. So it happens, I mean, reactants are much more favored than products. Okay, let's look at an example here. Find the pH of 0.75 molar of sulfuric acid. And it says, in sulfuric acid, there are two ionizable hydrogen atoms. What makes this molecule interesting is that its ionization constant for the first hydrogen, Ka1, ionized is significantly larger than is the second ionization constant, Ka2. The Ka1 constant for sulfuric acid is conveniently dubbed very large, while the Ka2 constant is 1.1 times 10 to the minus 2. It's actually still pretty big. As such, the sulfuric acid will completely dissociate into HSO4- in hydronium ions as a strong acid. So they gave us a bunch of information. The Ka1 that's dubbed very large, we're going to assume that it's complete dissociation. So if this is my concentration of sulfuric acid, I can also assume that that's going to produce the same concentration of hydronium ions. Because this first ionization this first protonation of water by sulfuric acid is 100%. It is a strong acid. So if I have an ice table, I'm starting off with 0.75. Again, water isn't included in this. I have 0 of these two entities. This is going to be 100% dissociation. So it's minus 0.75 and plus 0.75. So we're left with 0 concentration of H2SO4. So this is for Ka1. Now, what's going on with Ka2? Well, HSO4- has another hydrogen that's capable of being lost, so that you're left with just the sulfate ion in solution. Let's fill out the ice table with the information that we have. From the above ice table, we know that we're starting off with 0.75 molar of HSO4 minus, the hydrogen sulfate ion. We know that it's going to lose some. There is going to be some forward reaction because we're starting off with 0 concentration of the sulfate ion. And okay, we're not going to worry about the fact that there is hydronium in the solution. We're going to simplify it. So we're left with plus X. Okay, so that's our information that we have there. Let's switch up the color. So now we have Ka2 is equal to the concentration of sulfate, concentration of hydronium, over the concentration of the hydrogen sulfate ion. The question told us that it's 1.1 times 10 to the minus 2 for the Ka2 value. And we know that this is x times x, so x squared, over 0.75 minus x. Okay, let's do the 100 rule over here. 0.75 divided by 1.1 times 10 to the minus 2. I think we are above 500. Or below, I mean. Sorry, it is. So 68, which unfortunately is less than 500. So we have to do the long way. I'm going to erase this because I don't need it. Oops. Okay, so I have to do quadratic, and I always bring up the denominator first. So I get x, oh, I skipped steps here, x squared equals 8.75 times 10 to the minus 3 minus 1.1 times 10 to the minus 2 x. So when I rearrange this, I have x squared plus 1.1 times 10 to the minus 2 minus 8.75 times 10 to the minus 3 equals 0. And then you're going to do quadratic, and I get this. So obviously there's going to be only one real root, minus 1.1 times 10 to the minus 2 minus 0.182. That is not going to be a real root. It's going to give me a negative concentration, which is not possible. So I'm just going to do negative 1.1 times 10 to the minus 2 plus 0.182. And I get an x value of 0.0855 mole per liter. Okay, great. We are at this point, but what do I do now? Let's think about what we've done so far. We have the concentration of the original dissociation. This is from the first loss of protons. This is now my concentration for the second dissociation. They're in the same solution, so we can think of their concentration as being additive. So if I'm looking at, for the purposes of pH, because that's what the question's asking us for, I need to find what is the overall concentration of hydronium ion. Well, from my first dissociation, I have a concentration of 0.75 molar. And from my second dissociation, look at how much less I have. From the 0.7 molar of the hydrogen sulfate, I only produce 0.0855 molar more of hydronium from that dissociation, and it's because the first one is considered a strong acid and the second one is considered a weak acid. When I add these two together, I get a combined concentration of hydronium as being 0.8355 molar. Now, our pH. negative log of this concentration. And I get the very, very small number of 0.078. And let's put it into scientific notation, even though it looks a little bit weird for pH. Very small. Okay, and 2 significant digits. All right, now bases, unfortunately, they don't get much love in chemistry, in this course at least, because we focus so much on acids. So the characteristic taste of tonic water is due to the addition of quinine. That's actually interesting because they think that this might be, that is an anti-malarial quinine, and they think it might have some effect on the coronavirus as well. Quinine is a natural occurring compound that is also used to treat malaria. The base dissociation constant Kb for quinine is 3.3 times 10 to the minus 6. So it's a weak base. Calculate the concentration of hydroxide and the pH of a 1.7 times 10 to the minus, what is that? I think it's minus 3 mole per liter solution of quinine. Okay, so whenever, let's just use base plus water forms the protonated base plus hydroxide. Okay, so we know that the base is going to get a hydrogen. It's going to become hydrogen. It is going to have a hydrogen. It's going to become positive, and water is going to lose a hydrogen, become hydroxide. When I make my ACE table, it's 1.7 times 10 to the minus 3 here, and 0 for these two. Because it is only one hydrogen that's moving around, it's just plus x. And here, it's losing x. So they gave us the Kb value, but if we're writing it out, Kb is equal to the concentration of the conjugate acid times the hydroxide over the concentration of the base. So it's 3.3 times 10 to the minus 6 equals x squared over 1.7 times 10 to the minus 3. If you do, minus x. If you do the 500 rule, which is 1.7 times 10 to the minus 3 divided by 3.3 times 10 to the minus 6, we just eke by and we get 515, which voila, is bigger than 500. So let's scratch this x out. And then we finally don't have to do quadratic for one of them. So then I'm going to get x is equal to the square root of 1.7 times 10 to the minus 3 times 3.3 times 10 to the minus 6. And I get plus or minus 7.49 times 10 to the minus 5 molar. And obviously, we only want the positive root. So we can just think of that. This x represents the concentration of hydroxide. So what's wrong with this? pH equals the negative log of 7.49 times 10 to the minus 5. What's wrong with this? Well, we're using hydroxide ions to calculate using this. So this is not calculating pH, but pOH. I get a pOH of 4.3. And to find the pH, it's 14 minus 4.13. And I get a pH of 9.87. And voila. So again, very similar to what the calculating an acid is like. I think this is the last one I'm going to do with you. Pyridine is used to manufacture medications and vitamins. Calculate the base constant for, the base dissociation constant, so we're calculating Kb, if a 0.125 molar aqueous solution has a pH of 9.10. Okay, so if we are to write this out, what is this? C3H5N. What color do I want to use? I'll just use black. So if it's C3H5N, remember I was saying that these organic bases, they usually have hydrogen. We actually don't even have to write out this, but I'm showing you how it would work. That nitrogen, because of the lone pair of electrons, it's able to pick up one of the hydrogens and become an H plus hydroxide. Okay, so we at equilibrium, all right, we know that you know what, I'm going to write out the whole ice table. I'm bad, I like to skip steps, but then I forget, I confuse everybody. So we know this to be true, as well as our initial concentration being 0.125. My change is that we're moving to the right. And then I already have my information for X. I have my pH, which is 9.10. So let's over here. If my pH is 9.10, I can get to my concentration of hydroxide, but it requires a little bit of gymnastics, mathematical gymnastics. First, I have to find the pOH, 14 minus 9.10, which is going to be, come on, I should be able to do this in my head. 4.9. Okay, and so then I'm able to find my concentration of hydroxide by doing 10 to the power of negative 4.90, which I get 1.26 times 10 to the minus 5. So over here, I'm going to, instead of putting that X, I'm going to put in the information that I already know. It's 1.26 times 10 to the minus 5, 1.26 times 10 to the minus 5. And let's figure out what this value is. 0.125 minus 1.26 times 10 to the minus 5. 0.12, oh my goodness, 4987. Now I'm going to leave as many decimal points as I want and just round my final Kb value. So for my Kb, it's going to be my concentration of my conjugate acid and the hydroxide over the concentration of my base and this is going to be squared, right? They're both the same. So my concentration of my conjugate acid and my concentration of hydroxide, they're both equal to X. And so I'm just putting that there. And then I'm putting 0.124987. And I get a Kb value of 1.27 times 10 to the minus 9, which makes sense. It's a small number, 10 to the power of negative 9. If you get anything with a positive exponent, you did something wrong. Okay, and everything else you can try on your own. Oh, I don't see what's over here. But yeah, I just gave you guys space I even put the answers here for you guys to check. So try out those questions and see how they work for you. Good luck.